Welcome back to the deep dive. Our mission today is to get into a really fascinating or emerging infrastructure model. It's trying to solve one of the biggest problems in tech right now, the AI compute bottleneck. The subject is something called Project Prometheus, and its goal is basically to deploy these modular, hyper-secure AI data centers all across the globe.
That's right.
Now, if you are following this space at all, you know the demand for GPUs for training these huge foundational models for inference is just exponential.
It's staggering.
And the current way we build data centers, this kind of rigid, slow infrastructure, it just can't keep up. So Prometheus is proposing this worldwide network of self-contained GPU clusters.
Yeah, they're branding them as digital embassies.
Or black boxes.
Yeah,
I like that one.
me too.
The idea is to decouple compute from our old legacy power grids and, maybe more importantly, from geopolitical risk. But here's the really unexpected part. The framework we're using to analyze this huge, multi-billion-dollar AI challenge.
Crypto mining.
Exactly,
Yeah.
crypto mining.
And, you know, it's more than just a coincidence. It's really the foundational blueprint for this entire strategy.
How so?
The core problem that Prometheus is trying to tackle. I mean, where do you find cheap enough power, and how do you stop a government from just taking your stuff? That is the exact life cycle Bitcoin miners live through.
And live through violently. From a business perspective.
Oh, absolutely. Between, say, 2013 and 2023, they saw it all. The massive booms, the devastating busts, forced migrations, catastrophic losses of capital.
So our sources are basically suggesting that the big players in the AI industry were watching all this chaos
Taking very detailed notes.
and decided, okay, we have to build an anti-fragile compute fleet for the future. And the way to do that is to learn every single hard lesson the miners already paid for.
Paid for in blood, sweat, and billions of dollars in lost hardware.
So today, that's what we're doing. We're unpacking those lessons, seeing how they're shaping Prometheus's global strategy, and we're going to try to assess whether these digital embassies are actually the future of AI scaling.
Or if they're just doomed to repeat history.
Right.
We're really setting the stage for this grand, global, energy-driven race. I mean, you look at the locations Prometheus is considering. Nigeria, Oman, Chile, Iceland.
Not exactly your typical tech hubs, not Silicon Valley.
Not at all. These are energy-rich nations that, and this is the crucial part, have power that the developed world either doesn't need or, frankly, can't afford.
So the whole premise, then, rests on successfully managing a kind of geopolitical risk that all the previous digital arbitrage players just completely failed to navigate.
That is the multi-billion-dollar question.
Okay, let's just dive right into that.
Yeah.
Because when you strip everything away, when you look past the fancy technology, the high-end GPUs, the custom silicon, you realize these ventures aren't really technology businesses at their core.
No, at all. There's something much, much older.
They're energy arbitrage plays.
Precisely. They are fundamentally pure energy arbitrage, just, wearing a very expensive, very technologically advanced suit.
That's the first really striking point from the sources, and it just forces you to look at this whole industry through a completely different lens.
It does.
Whether you're running a server farm to mine Bitcoin, or you have a modular cluster that's training the next big LLM, the basic economic driver is identical.
It's all about finding the cheapest, most abundant source of power you can possibly get your hands on.
And that's the definition of the economic model for both of them, right?
Absolutely. The cost of electricity is the dominant operating expense. We're talking, it often represents 70% or more of your ongoing cost of goods sold.
Wow, 70%.
So for crypto mining, profitability was measured really simply. What's your hash rate divided by your energy cost? That's it.
And what was the magic number they were chasing?
Historically, miners were successful if they could chase a break-in buy price that was somewhere between, say, 3 and 6 cents per kilowatt hour.
So like a third of what I pay for power at home?
Or less. If they couldn't hit that number reliably, they were simply outcompeted and went bankrupt.
And so for Project Prometheus, this AI infrastructure model, it's running on the exact same constraint.
The very same. They just have a slightly higher tolerance for cost.
Why is that?
Because their end product, specialized AI compute, it commands a much higher price than a fungible commodity like Bitcoin.
Got it. So how do they measure their competitiveness?
For AI, it's all about compute capacity. You might quantify it in dollars per GPU hour, or TFLOP, tera floating point operations per second.
Okay.
And that number has to be divided by the energy cost. The sources are indicating that AI operators, because of all the specialized hardware and the need for better networking, they're targeting prices below 7 cents per kilowatt hour for the model to be viable.
So still incredibly cheap. If they're paying what you or I pay for residential power in the US or Europe.
The whole model collapses, the margins just disappear.
So if that profitability threshold is so razor thin and it relies completely on finding super cheap energy, what does that immediately dictate about your business strategy?
It dictates where you go. It dictates your geographic migration pattern. This is really what's inside of the whole thing.
Right.
Both of these business models only work if your energy costs are dramatically lower than the market rates in developed countries. You are forced to look outside the traditional tech hubs.
Which leads us to the identical playbook you mentioned earlier.
The stranded energy monetization playbook.
Let's get into that because it's fascinating. It's all about chasing waste energy or stranded energy and turning something that's otherwise economically useless into a premium digital product.
And the crypto miners, they became absolute masters of this.
Right.
I mean, just think of the early waves of crypto migration. Wave one was Iceland between about 2013 and 2018.
What was the resource there?
Iceland's geological gift.
Yeah.
They have massive geothermal and hydro surpluses. That power is reliable, it's renewable, and crucially, it's really difficult to export efficiently from an island.
So the miners came in and turned that local power into Bitcoin, which is very easy to export.
Exactly. Then the next big wave was the migration to China, which, for a while, was the undisputed global center of mining.
And that was all about seasonal power, wasn't it?
The Sichuan experience from about 2015 to 2021 is the perfect example. Sichuan has this immense hydropower capacity, but the local grid couldn't use all of it during the rainy summer season.
So the power was just being wasted.
It was either curtailed, meaning they just turned the turbines off, or simply wasted. So the miners rushed in, and they acted as this high-volume temporary consumer for that power at ultra-low wholesale rates.
And at its peak, what percentage of the network was in China?
We're talking between 65 and 75% of the entire global Bitcoin hash rate. It was a massive concentration.
And we still see this playbook today in places like Texas.
Oh, absolutely. Texas has this huge wind oversupply. Sometimes when the wind is blowing at night, it can actually cause negative pricing on the grid because generation exceeds demand.
So they're literally paying people to take electricity.
And the miners act as these dynamic sponges. They soak up that surplus, they help stabilize the grid, and they turn otherwise worthless electricity into digital value. We also see it in Siberia or Kazakhstan with flare gas.
That's the natural gas they burn off in oil wells, right?
Exactly. It's uneconomical to build a pipeline, so they just burn it. Miners put a container right next to the wellhead and power their computers with it.
Okay, so that's the crypto playbook. How closely does the target list for Project Prometheus copy this strategy?
It's uncanny. It is the identical strategy. They're just turning waste energy into AI compute instead of Bitcoin.
For example.
They're targeting Iceland's geothermal and hydro surplus, the exact same resource the miners maxed out a decade ago, but now for a much higher value product.
What about the flare gas?
They are prioritizing Nigeria's massive flare gas reserves. This gas currently just burns, polluting the atmosphere and providing zero economic value. If Prometheus can capture that gas at the source, they eliminate transportation costs and get power for basically the environmental cost of capturing it.
That's a powerful narrative. What about other regions mentioned in the sources, like South America?
They're looking very closely at places like Chile, specifically because of solar curtailment.
Too much sun.
Literally. Chile invested heavily in solar, but their transmission infrastructure hasn't kept up. So during peak daylight hours, they produce more solar energy than the local grid can handle, and they have to force generators to turn off.
That wasted solar power is a gold mine for an AI operation.
It's a gold mine. Similarly, they're targeting Norway's very consistent hydro surplus and Oman's vast, cheap gas generation capacity.
So the core lesson here is that the infrastructure has to follow the energy, not the other way around. But this is the big question. If they're chasing the same cheap power in the same kinds of places, what makes Prometheus any less vulnerable than the miners who eventually got kicked out?
And that's where the preemptive planning comes in. See, the history of crypto mining is just a series of these migration waves, Iceland and China, Texas, Kazakhstan, all driven by chasing these temporary energy policy openings.
They were reactive.
Completely reactive. Prometheus has analyzed this boom-bust migration cycle, and they're trying to preempt the bust part through really sophisticated geopolitical portfolio management.
What does that look like in practice?
They start with friendly, stable countries. That's phase one. Think Oman and Chile. Then they move cautiously into higher capacity, but maybe riskier emerging markets. That's phase two, like Nigeria.
Oh, man.
Then they constantly optimize the global load distribution. That's phase three. They know the energy arbitrage window in any single location is finite. It will close.
So it sounds like they're treating cheap electricity like this resource that's not fixed but constantly moves around the globe.
That is precisely the realization. It's not permanent. It's an arbitrage, and all arbitrage opportunities close once the market, or more likely, the government catches up.
So the key is to be portable enough to move when that window inevitably slams shut.
Exactly. You have to be able to pack up and leave.
That idea of portability, that leads us right to the technical architecture. We've established the economics are identical, so let's look at the physical solution. The core architecture that Project Prometheus is using, these modular, containerized pods, was entirely pioneered and proven effective by crypto miners.
Yeah, it was.
So why are they choosing this design? What are the really deep financial advantages that make it worth all the complexity?
Well, the use of the standard ISO 40-foot high cube shipping container as the sort of basic building block for your compute capacity, that's the genius of the model.
And what did a typical crypto mining container look like?
A crypto container, it usually pulled about 200 to 400 kilowatts of power. They were designed for ultimate simplicity. You know, plug and play, you could have them operational in days, and you could ship them easily on any container freighter in the world.
Now, how does the Prometheus AI pod differ technically? I mean, given the sheer power demand of modern AI hardware.
It differs dramatically in density. The physical envelope is the same. It's still a 40-foot container, but the internal engineering is just vastly more complex.
How much more power are we talking?
These AI pods, they draw between 1,000 and 2,000 kilowatts. That's 1 to 2 megawatts of power.
Wow.
So that is 5 to 10 times the power density of a typical mining container. And this density increase is absolutely essential because a single NVIDIA H100 GPU just pulls an immense amount of power compared to an old ASIC miner.
That kind of extreme power density must make cooling an absolute nightmare.
It is the defining technical challenge of the whole thing. But the reason for choosing that identical shippable form factor, it remains the same. It's identical economic pressure. You need speed, you need portability, and you need capital efficiency.
Right. If you need capacity today, not 3 or 4 years from now.
You need a standard unit you can mass produce in a factory, ship quickly, and deploy on-site in a matter of days or weeks.
So let's really dig into the decisive financial advantages of modularity. Because this is where the business case for Prometheus truly separates itself from, say, a traditional data center build. Let's start with speed to market.
Speed is the absolute AI imperative. I mean, we're in a race where every month you lose to a competitor could mean, corporate death. Waiting 4 years for your infrastructure is just a guaranteed loss.
And a traditional hyperscale data center, what's the timeline on that?
You're looking at land acquisition, permitting, customized construction, commissioning. It takes 36 to 48 months to become fully operational.
That's a non-starter in the current AI climate.
It's completely unworkable. The modular timeline, it completely disrupts this. By manufacturing the pods in parallel in a controlled factory environment, shipping them globally, and then doing rapid on-site assembly, they can go from a go decision to generating their first dollar of revenue in only 8 to 10 months.
And the sources actually quantify the financial impact of that speed advantage. It's staggering.
It is. The opportunity cost you save is just substantial. If you model, say, a 10 megawatt deployment, every single month of delay costs the operator between $1 and $2 million in lost revenue.
So over the full life cycle of a traditional build,
you're looking at an estimated $40 to $76 million in pure opportunity costs that you've saved just by choosing the modular route.
So if an AI startup needs training capacity for a big model launch that's scheduled 18 months from now, the traditional path means they're ready long after their competitive window has slammed shut.
While the modular path ensures they can meet their deadlines and start generating revenue immediately, timing is everything in AI.
And beyond speed, modularity transforms capital efficiency.
Oh, massively. A traditional 50-megawatt hyperscale build requires this huge sunk capital commitment on day one. We're estimating between 260 and $370 million.
With zero return on that for years.
Exactly. It's a huge fixed risk that requires immense upfront financing.
Where's modular deployment?
It allows for phased, incremental investment. You only deploy the capacity as your demand is validated. You might deploy 10 megawatts in year one, another 10 in year two, and so on.
So you dramatically reduce your upfront risk exposure.
You avoid that massive sunk cost. And critically, your revenue starts flowing in year one, which significantly improves your cash flow.
The net present value analysis on this must be pretty stark.
It is. The financial modeling shows that because you get faster revenue generation and you have the ability to reinvest your early profits, a modular build maintains a higher net present value advantage of over $140 million compared to a traditional build, just over a 5-year period.
So lower risk, faster cash flow, and higher overall returns.
You got it.
But the truly decisive advantage, the one that justifies all the operational complexity we're going to talk about later, is the relocation capability.
The $700 million insurance policy.
Let's unpack that.
This is the core geopolitical lesson learned from the China ban. They witnessed the catastrophic loss that was incurred by miners who had built traditional fixed infrastructure. So let's just walk through the traditional failure scenario.
Sure.
A host country, let's say it's Kazakhstan, bans operations or jacks up power tariffs to a prohibitive level.
What happens to the operator?
The operator loses everything. $260 to $370 million in sunk capital. The buildings, the fixed power infrastructure, it all becomes a worthless, seized asset. You add the revenue loss on top of that, and the total 3-year impact can be over $1 billion.
The total write-off.
A complete write-off. Now, compare that to the modular recovery. Prometheus models this scenario. The government institutes a ban.
What do?
They trigger the remote kill switch, which we'll get into, secure the pods, and relocate. The beauty of the containerized form factor is that the relocation costs are minimal, maybe $2 to $5 million for disassembly, shipping, and reassembly at a new friendly port.
And how long does that take?
Full operations can be resumed in about 15 weeks, so around 90 days. The actual loss is limited to the revenue you lost during that 3-month downtime, plus the relocation fees. You're talking about maybe $6.5 to $11.25 million.
That difference is astonishing. You're mitigating a potential billion-dollar loss for the price of about $11 million. It literally is an insurance policy.
And that massive avoidance of catastrophic loss, it's actually been quantified by actuaries as having an expected value of $63 million over the life of the facility. That's why portability is built-in insurance against energy nationalism and political instability.
Let's shift back to the technical agility this architecture enables, specifically around cooling. You mentioned that density requires radically different thermal management.
Yes. AI infrastructure is following crypto's cooling playbook, just with a 3 to 5 year lag. Crypto miners were the true pioneers in things like immersion cooling. They were achieving these ultra-low power usage effectiveness numbers, or PUEs, as low as 1.05.
Okay, let's quickly define PUE for our listeners. It's a term we use a lot, but what exactly are we measuring?
Right. PUE, power usage effectiveness, is basically a ratio. It's the total power consumed by the entire facility divided by the power that's actually used by the compute equipment itself.
So a perfect score would be 1.0.
A perfect score is 1.0. If your PUE is 2.0, it means you're wasting half your power on non-compute overhead, like cooling systems and lights. A PUE of 1.15 means only 15% is wasted. Lower is always better.
Got it. So AI operators facing these incredibly dense GPU loads, they're now being forced to adopt these advanced cooling methods.
Exactly. Prometheus is currently deploying direct-to-chip liquid cooling systems to manage the intense heat that comes off of modern GPUs. Their current design is targeting PUEs around 1.2 to 1.3.
Which is pretty good for the industry, right?
It's a respectable industry standard, but it still lags behind what the best immersion crypto operations were doing. But critically, they're already fast-tracking R&D into full immersion cooling.
Now, what's the target there?
They're targeting best-in-class PUEs below 1.15. And this cooling efficiency is just so crucial because every fraction of a cent per kilowatt hour they save gets multiplied across millions of GPUs.
Okay, what about the constant hardware refresh cycles? The GPU market doesn't stand still. We get a new generation every 18 to 24 months. How does modularity make this hardware churn manageable, especially compared to a traditional facility?
Traditional data centers suffer a massive penalty here. When a new generation of chips arrives, say the next H series or B series, upgrading the facility is this huge logistical nightmare.
What does it involve?
You have to plan a 6 to 9 month shutdown window to decommission all the old equipment, rip out the old cooling systems, and then install the new stuff.
That sounds incredibly expensive.
It costs over $150 million in lost revenue per refresh cycle, and it guarantees massive customer churn. I mean, no AI client can afford 9 months of downtime.
So the modular architecture allows for continuous operation, completely eliminating that costly gap.
That's the key technical advantage. Because the GPU compute modules are contained within these standardized hot swappable sleds inside the container pods, Prometheus can perform rolling upgrades.
How does that work?
They order the new hardware, ship the new sleds to the site, they migrate customer workloads to an adjacent available pod, and then they just simply swap out the old sleds for the new ones.
So from the customer's perspective, there's no downtime at all.
Zero customer downtime is achieved.
That seems like an unparalleled competitive edge in a market where technology obsolescence is probably the biggest single threat.
It's truly existential. The sources estimate that the total cost of a full refresh cycle for a 50-megawatt facility, factoring in the resale value of the old hardware and all that lost revenue, is estimated to be $690 million cheaper using the modular approach compared to the traditional disruptive path.
$690 million cheaper.
Yeah. We are talking about a cost reduction percentage in the high 90s.
That ability to be technologically agile, combined with the geopolitical insurance, it really starts to build a powerful case for why Prometheus has to be modular. There's no other way.
It's the only way the numbers work. Now, if we connect all these dots back to the biggest failure of the crypto industry, which was policy reversal, we realize something important.
What's that?
Having identical economics and identical technology means that Prometheus is inherently vulnerable to the exact same governmental reactions.
Right.
Therefore, the critical difference has to be their ability to secure political longevity. And they have studied crypto's geopolitical failures meticulously.
Okay, let's analyze those failures in depth. Let's start with case one. Iceland's reversal back in 2018. It seemed like the perfect environment, cheap, green energy, but then the government capped new industrial power supply. What went wrong?
The failure was fundamentally one of optics and value creation. Iceland is a small country, and the concentration of miners just became overwhelming.
They were too visible.
They were highly visible, and they were using a national strategic resource, that cheap, clean power, but they were creating minimal local economic value.
These are lights-out facilities, right?
Exactly. They need a couple of security guards, maybe a few maintenance techs, but very minimal specialized labor. So the narrative in the country quickly shifted to, these foreigners are using our power for speculation.
Which created the perfect environment for energy nationalism.
Exactly. Energy nationalism is that moment the government realizes electricity is a finite strategic resource and decides it should be reserved for domestic industry.
Like an aluminum smelter, which hires hundreds of people.
Right. An aluminum smelter instead of these invisible foreign-owned tech operations. The miners had completely failed to secure a social license to operate.
Okay, case two, the devastating China ban in 2021. That took over half the global hash rate offline in a matter of weeks. The stakes there were much higher.
They were. The Chinese government had three main concerns that mining directly undermined. First was capital flight. Crypto was a way to get around their stringent foreign exchange controls.
What was the second?
Power shortages. Mining was drawing immense power from local grids, and that was impacting major cities, especially during the dry seasons when the hydro wasn't running at full capacity.
And the third, the critical one.
Mining, even when it was using seasonal hydro, it undermined their national carbon commitments and, more importantly, their centralized economic planning.
And since mining had no powerful domestic friends, no political cover.
It was an easy, high-impact target to eliminate.
And finally, Kazakhstan's whiplash. They welcomed all the exiled miners after the China ban, but then they rapidly imposed crippling restrictions.
Kazakhstan really exposed the risk of grid fragility and just short-sighted policy. The government welcomed them purely for the expected tax revenue, but they did it without any planning for the infrastructure impacts.
Still happened.
The miners pushed an aging, brittle electrical infrastructure past its breaking point, and it caused widespread blackouts. And when the promised tax revenue didn't quite materialize, and the public started experiencing those blackouts, the political will just vanished overnight. It led to immediate power restrictions and another mass exodus.
So Prometheus's risk mitigation strategy is a direct, tailored counter to every single one of those catastrophic failures.
It is.
So how do they hedge against the concentration risk that plagued the miners in Iceland?
They institute a very strict portfolio management rule. They will never exceed 30% of their total global capacity in any single country.
So that diversification acts as a kind of firewall.
It's a firewall. If a host country fails, the global service continues uninterrupted, and that capacity can be rapidly shifted to one of the 7 other deployment sites. This isn't insurance against technical failure, it's insurance against political failure.
And to counter the China problem, that lack of political cover, Prometheus is building what the sources are calling the social license mode.
This is maybe the most critical philosophical difference between them and the miners. Prometheus is intentionally trying to transform the narrative from extraction to technology partnership.
They're not just taking cheap power.
Right. They're promising a strategic input for that host nation's own digital future.
And how is this achieved in practice? I mean, what are the specific commitments that actually buy you that social license?
They achieve it through specific enforceable commitments that are detailed right in their operating agreements. Things like building local AI training and certification institutes,
What else?
setting aggressive local employment targets, maybe 20 to 30% of the non-technical workforce, and dedicating 0.5% to 1% of the local site revenue to community investment schools, infrastructure upgrades, things like that.
That fundamentally changes the political calculus for a local leader. Instead of a politician banning foreign speculators, they're now perceived as shutting down a local technology institute and some of the highest paying jobs in the region.
Exactly. They create a powerful domestic political cost for expropriation. Plus, they mitigate the carbon backlash that China faced by prioritizing green energy.
How so?
They're targeting a portfolio mix that is 60% or more sourced from renewable or hydro resources. They're not just greenwashing, they're using the flare gas and the solar curtailment precisely because those are often the cheapest and the greenest stranded assets available.
Let's talk about the legal armor they are pioneering. The digital embassy model. This seems crucial for securing the crown jewels, the AI models, and the advanced GPUs from any foreign interference or seizure.
The digital embassy model establishes very clear legal sovereignty boundaries. The host nation agrees that while they own the land and they control the perimeter, they explicitly waive all logical access rights to the data or the equipment inside the containers.
And this is all codified in an agreement.
It's codified through something called a Sovereign Enclave Hosting Framework Agreement.
And how does this relate to international regulations, specifically something like U.S. export controls?
It's absolutely crucial for compliance. By deploying these advanced U.S. origin chips, like the NVIDIA H100s, in potentially sensitive regions, Prometheus has to prove that the U.S. government's BIS regulations are being followed.
The Bureau of Industry and Security.
Right. They have to ensure that the AI operator Prometheus retains sole, absolute control and custody of those advanced chips. This prevents any unauthorized transfer of technology. The digital embassy status is meant to provide a legal buffer against mandatory logical access by the host government.
This brings us back to the ultimate threat, though. Energy nationalism.
Yeah.
If electricity is the new oil, then eventually the host nation is going to realize they are giving away immense value.
Absolutely. Prometheus knows that this window is finite. They have to mitigate that growing narrative that cheap power should be reserved for domestic industry.
So their strategy is to turn future owners into present partners.
Yeah.
How do they do that?
They plan to use build, operate, transfer models, or BOT models, after a defined period, say 10 to 15 years.
What does that mean?
It gives the host nation the contractual option to purchase the pods and the facility, transitioning it into a domestic, state-owned AI resource. They also establish joint ventures, giving host nations 10 to 20% equity in the local operations right from day one.
Ah, so that makes the host country a shareholder.
A shareholder.
Okay.
It incentivizes them to protect the asset rather than seize it.
So if the government decides to raise the power price, they are effectively raising the power price on their own equity stake.
Mm-hmm.
That's a powerful internal incentive.
It is exactly that. It's structural risk mitigation. They are trying to build a partnership that makes the host nation a political and a financial co-beneficiary.
So we have the economic reason, which is arbitrage, and the political reason, which is this modularity and social license. Now let's talk about logistics and security. How does Prometheus actually ensure continuous operation and critically security in these remote, potentially high-risk locations? How do they make sure the black box stays black, especially when they're facing high-level security threats?
The entire operational model relies on this concept of the sovereign enclave. The framework agreement defines the physical boundary. The host country provides the socket.
The socket.
The socket. That means the medium voltage power intake, we're talking 10 to 35 kilovolts, the redundant dual diverse fiber conduits, the concrete foundation pad, and the perimeter fencing.
And Prometheus manages everything inwards from that
Right.
point.
Exactly. Everything inside that fence ensuring its integrity.
But operating in such high-density environments, especially with advanced cooling and power systems, that must inherently raise significant health and safety risks, right? For the local environment, for first responders.
That's a major design consideration. I mean, we are talking about extreme high voltage intake, high DC currents feeding the GPUs, and significant chemical hazards.
Like what?
The cooling systems use these dielectric fluids or specialized glycols, and the battery energy storage systems that support the facility, they contain powerful lithium-ion packs. There's a real electrolyte leakage risk.
That sounds like a major liability if something goes wrong.
It is. So mitigation requires full transparency and joint planning with the local authorities. They mandate things like containment berms around the cooling systems and the battery units to capture any leaks.
And what about the people?
More importantly, they require a mandatory certified training program for local staff and local emergency responders, police, fire, HUZ-mate teams.
So they have to know what they're dealing with.
These teams need to be trained on the specific hazards, the high-voltage lockout procedures, and they need integrated emergency response plans, including annual joint drills. You can't just drop this kind of complex technology into a remote region without ensuring local safety awareness.
Okay, shifting to security, the logical and physical risks must be amplified when you're dealing with state-sponsored espionage in some of these new jurisdictions. What are the major threat vectors they're anticipating?
The threats are sophisticated and they're layered. You have state-sponsored espionage trying physical tampering, opening up the containers to install listening devices or steal chips.
Sure.
Supply chain compromise is huge. Hardware trojans being inserted into the equipment before the pod is even sealed and shipped.
And the third?
And finally, the compromise of the remote control plane, which would allow a hostile entity to take over the entire compute environment logically.
So what are the defense mechanisms that are layered into this black box architecture?
It's a trust but verify model. Physically, the containers are protected by hardened steel, internal vibration sensors, and tamper-evident seals. Access requires highly specialized multi-factor biometric authentication.
Like what?
Fingerprint plus retina, which are then cross-referenced with the Remote Security Operations Center, or SOC.
And the host nation is allowed to verify this physical sanctity even if they can't access what's inside.
Yes. This is a crucial compromise. Prometheus maintains an immutable, cryptographically signed transparency log of all physical access attempts, right down to the second.
And the host nation can see this log.
The host nation is granted read access to this specific log, which proves that the physical boundary has been maintained. If the log shows a breach, the host nation has verified proof that Prometheus failed. If the log shows only authorized access, Prometheus has verified proof that the host nation maintained its boundary control.
That's a very clever way to handle mutual distrust. But let's talk about remote sovereignty enforcement. How do they maintain control and operational continuity when the terrestrial fiber links inevitably fail, or worse, are intentionally severed?
This is where out-of-band management becomes absolutely vital. The primary management link uses these encrypted, dual-diverse fiber conduits, but the crucial backup is over encrypted satellite channels.
Like Starlink or OneWeb.
Exactly. This provides a completely independent path for monitoring and issuing critical control commands. It ensures the facility can be controlled and secured even during a country-level internet shutdown.
And now the final line of defense, the nuclear option against a catastrophic seizure, the remote kill switch.
That is the ultimate geopolitical deterrent, the remote kill switch and crypto shredding protocol. If Prometheus detects a major physical breach or an expropriation attempt or some disaster that compromises data integrity, a secure, authenticated command is issued from their global orchestration layer.
And what happens then?
Within 60 seconds, the system securely and irrecoverably erases all of the encryption keys that are stored in the hardware security modules, the HSMs.
So the data is still there, but it's unreadable.
Since all the customer data is encrypted using these keys, deleting them instantly renders all of that stored data permanently unrecoverable. The physical asset, the GPUs and the container, is still there, but it is now technologically worthless to the hostile entity in terms of accessing customer IP or proprietary models.
That transforms the asset from something incredibly valuable to seize into something that has to be returned to avoid the total destruction of its logical function.
It creates a very powerful disincentive. The only way to get that asset to work again is through cooperation with Prometheus to reinitialize it.
Beyond security, running a massive global distributed fleet must require immense operational efficiency, especially in remote areas. This is where AI-driven operations and robotics come into play. Walk us through the automation capabilities.
The global orchestration platform is the brain of the entire fleet. It's not just managing one data center. It's managing workloads across potentially dozens of pods distributed across multiple countries. It uses advanced AI orchestration for workload intelligence predicting job needs and, critically, carbon-aware scheduling.
And let's pause on carbon-aware scheduling. This is fascinating from both an ESG perspective and a cost perspective.
It is. The platform dynamically routes any latency-tolerant workload, so think long batch training jobs, to the greenest and cheapest pods at any given moment.
Give me an example.
For example, I might route jobs to Norway when their hydropower is abundant and the pricing is low, or to Chile during those periods of solar curtailment we talked about.
And what about latency-sensitive jobs?
Conversely, latency-sensitive inference jobs might be routed to a more expensive but closer facility in Oman or Iceland. This optimization is constant, maximizing cost savings and meeting those ESG commitments simultaneously.
That is a huge step up from traditional fixed data center scheduling. And how does the system manage maintenance remotely? You can't just fly an engineer to a remote Nigerian flare site for every small technical issue.
And that's the job of the lights-out robotics. The pods are designed to be almost entirely autonomous. They're equipped with autonomous guided carts, or AGCs, and specialized 6-axis robotic arms mounted on internal rails.
And these systems do what?
They perform all the routine tasks: hot-swapping faulty GPU sleds, conducting visual inspections using internal cameras, and managing simple component replacement.
So if a fan fails in a remote location, a robot handles it.
Precisely. This enables true lights-out operation, which reduces the dependency on highly specialized, expensive local staff.
And what about for those rare, complex scenarios that still need a human?
For those, they use an augmented reality interface. A local technician, and this is likely facility or security staff, not a specialized engineer, wears AR glasses. A remote expert overlays diagrams, step-by-step instructions, and diagnostic data right onto their live video feed, guiding them through the complex repair.
So the core principle is minimal dependency on local, specialized labor.
Exactly. It mitigates skill scarcity and high operational costs.
Okay, so we've established that modularity provides speed, geopolitical insurance, and technological agility. But complexity always comes with a cost. This global, hyper-secure, robotic fleet, it can't be a silver bullet. What are the major disadvantages? What's the modular management tax?
The sources outline some really significant trade-offs that have to be factored into the total cost of ownership. The first one is just raw operational complexity, and that manifests directly in higher labor costs.
Yeah, I would imagine managing 8 distributed sites across 8 different countries is radically more difficult than managing one giant building.
It is. It requires 25 to 50% higher annual labor costs. Managing security, logistics, and maintenance for a distributed fleet is just flat out more expensive.
What kind of numbers are we talking about?
We're talking about maybe $10 to $15 million annually for the modular setup, compared to the $8 to $12 million required for a centralized facility of the same capacity. This is the direct cost of that geographical diversification.
And that complexity has to multiply across regulatory frameworks. That must be a massive administrative burden.
The regulatory friction is perhaps the largest administrative cost center. The compliance burden for 8 jurisdictions is 5 to 6 times more expensive annually.
Because you're managing 8 sets of everything.
8 sets of data protection laws, 8 differing tax regimes, 8 sets of labor law frameworks. The sources estimate this costs around $3.15 million per year versus only about $550,000 for a single-site traditional build.
And taxes must be a nightmare.
You also have to manage complex transfer pricing studies for every single country, which is a significant tax challenge that requires constant legal and financial oversight.
Let's address the physics constraints that modularity can't fully overcome, specifically the efficiency penalty.
Yes. Modular pods, they have a slightly worse power usage effectiveness, a slightly higher PUE than an optimal traditional megascale center.
How much worse?
The delta is about 0.05 to 0.15 PUE points worse, which means 4 to 12% higher energy overhead, even with advanced liquid cooling.
And why is that?
It's because small distributed cooling systems are just inherently less efficient than a single, centralized, optimized chilled water plant in a massive hyperscale facility. It's an economy of scale thing.
And what does a 0.05 PUE delta actually translate to in real-world energy cost?
For a large 50 megawatt deployment, this small efficiency penalty, when you multiply it across a year of $2.6 million annually in energy, especially if you're in a hot climate where cooling demands are higher.
So that slightly erodes the massive energy savings they gain from the arbitrage.
It does, though it certainly doesn't negate them.
And finally, performance. If I'm a customer trying to run a massive, synchronized AI training job, does that physical separation between pods impact my speed?
It absolutely does. And this is the key technical performance trade-off that really determines which customers Prometheus can serve. Modular deployment, because it involves linking containers together over fiber, it adds 50 to 200 microseconds of interpod latency.
Is that a lot?
For most standard cloud applications, no, not really. But for ultra-low latency applications, think high-frequency trading, where microseconds are millions of dollars, or for training the world's largest foundational AI models that require perfect, instant, all-reduced communication between thousands of GPUs, this penalty is disqualifying.
How much does it slow things down?
The sources note that a typical 30-day training run can be slowed by up to 4.5 days, just due to this accumulated latency penalty.
So this is strategic weakness. Prometheus cannot serve the absolute highest-end, most latency-sensitive clientele.
Correct. So what does all this complexity and these trade-offs mean for their overall deployment strategy? The source material provides a really clear strategic fit matrix.
So when does modular dominate?
Modular is the correct choice when 3 factors align. First, time to market is absolutely critical, like in the current AI race. Second, the political risk is defined as high say, greater than a 5% probability of disruption in the short term.
And the third?
Third, when those energy arbitrage opportunities like flare gas are available and substantial. And finally, when export control compliance is needed, requiring that black box deployment of advanced chips like H100s into restricted markets.
And traditional hyperscale still holds the crown in specific niches.
Traditional wins only when 2 conditions are met. You need megascale, greater than 200 megawatts, in a single, perfectly stable OECD country like Norway, where political risk is negligible. Or when that ultra-low latency is absolutely non-negotiable, for example, for HFT firms who are willing to pay a 5 to 7 times premium for proximity and 0 latency penalty.
For everyone else, modular seems to provide better risk-adjusted returns.
It does.
So Prometheus isn't putting all their eggs in the container basket. They're blending these deployment options to build what they call an anti-fragile portfolio.
This hybrid deployment strategy is the pragmatic approach. They aim to use traditional land-based and brownfield repurposing models for their foundation, making up about 80% of their total capacity.
Why that approach for the majority?
Because it offers the best cost and scalability once a site is proven to be stable. Repurposing old power plants is especially attractive, as it gives them immediate access to existing pre-permitted grid connections, saving them years of delay.
What about the remaining 20%? That's where the insurance comes in.
Yes, a strategic hedge of about 10% is dedicated to maritime-based pods, so vessels placed at a port. This is the ultimate mobility and evacuation insurance.
A literal floating data center.
Being on a ship allows them to relocate an entire data center fleet in a matter of weeks, bypassing complex land rights, local permitting, and political seizure entirely. It's the ultimate get-out-of-jail-free card.
A literal floating digital embassy.
Exactly. And the remaining 10% is dedicated to what they call ESG leaders. Co-location with dedicated energy sources, like flare gas capture or being right at a hydro dam.
And that's the ultimate arbitrage play.
The lowest possible power cost, and it generates that crucial environmental and social narrative. This blend ensures that the failure of any single pod or country does not affect the overall service. They're aiming for 99.99% portfolio availability through this automated workload routing.
Which brings us full circle. Project Prometheus is fundamentally solving the exact same physical and political problems that crypto mining faced a decade ago, that need for cheap, decentralized power. But they are armed with these crucial advantages.
Better timing.
Better customers.
And, most importantly, a meticulously engineered social license.
The final assessment from the sources seems pretty clear. The modular strategy is validated by crypto's successes, the immense margins you can get from energy arbitrage, and the proven portability of the ISO container.
But Prometheus meticulously avoids its fatal flaws. The lack of a social license, the concentration risk, and the purely speculative nature of its end product.
And when you total up all the costs, the TCO analysis is really the ultimate proof of concept. Despite paying that modular management tax, those higher annual labor and compliance costs, the modular approach still yields a 25% lower total cost of ownership than a traditional build over a 5-year period.
The savings are just dominated by the three factors we've been discussing. Massive energy cost savings from arbitrage, the huge financial advantage of technology refresh agility, that ability to hot swap GPUs with zero downtime, and the quantifiable value of that geopolitical insurance, the ability to relocate and avoid $1 billion write-off.
So the ultimate lesson from crypto, and really the core vulnerability for Prometheus, it all hinges entirely on speed. The first wave wins the arbitrage and secures the power.
But the second wave gets crushed when energy nationalism inevitably takes hold.
And that window for Prometheus to fully deploy its diversified portfolio, to secure its energy contracts and establish its social license, it's estimated to be short.
Very short, likely only 3 to 5 years.
Before what happens?
Before these host countries inevitably realize they are giving away a strategic asset, their electricity, for a fee. Once that host country develops its own sovereign AI capabilities, that strategic asset becomes far too valuable to share.
So the question isn't whether the model works. We know it does. It's whether AI infrastructure can move fast enough to secure its global footprint before governments decide electricity is simply too strategic to share. That race against the political clock is what will define the next decade of AI scaling.